Okay, today we're going to look at right triangle trigonometry. Right triangle trigonometry. If you remember, we looked at the trigonometric functions, sine, cosine, tangent, cosecant, secant, and cotangent based on what the other day? The unit circle, right? We said cosine was the what? X coordinate of that point. Sine was the y coordinate, and then we had definitions based on the x and y coordinates of that point. Today we're going to look at a right triangle, and we're going to define these trigonometric functions. So, what do we know about a right triangle? What does it mean? What does the word right triangle mean? What does that mean? Anybody know? Yes. It has a 90-degree angle. 90-degree angle. That's what that square means. That angle is 90 degrees. If we have, let's say, some angle theta, okay, then from this angle theta, this is called the opposite side. This is called the adjacent side. And this long leg here, the longest leg, is called the hypotenuse. Okay? And here, we need to mention that theta is an acute angle. What does acute mean?
Less than 90.
Between 0 and 90 degrees, acute angle. So, based on knowing that this is our theta, we can find sine theta. Sine theta is defined to be the opposite side over the hypotenuse. Cosine theta is defined to be the adjacent side over the hypotenuse. Tangent theta is defined to be the opposite side over the adjacent side. Okay? We can get our reciprocal functions. Cosecant theta is hypotenuse over opposite. Secant theta is hypotenuse over adjacent. And cotangent theta is adjacent over opposite. Okay? So we have our 6 trigonometric functions based on this idea of a right triangle. Now, we have a theorem that I'm sure we have all seen, the Pythagorean theorem. We've all seen that one, right? Pythagoras came up with this theorem, as well as other properties. But the Pythagorean theorem states that the hypotenuse squared equals the opposite side squared plus the adjacent side squared. Okay? That's our Pythagorean theorem. And we can use this to solve right triangles. We may have some components given, and we may have to find the other components. Well, if we're given 2 of these components, we can find the other component by what? This Pythagorean theorem. So let's look at an example. Let's look at an example. We want to use the triangle, and we'll draw the triangle in a minute. To find the exact values of the trig functions of theta. So we have a right triangle. This is our angle theta. They tell us that the hypotenuse is 13 and the opposite side is 5. We don't know what that adjacent side is. We'll call it x. So they want us to find the 6 trigonometric functions based on what we see in this triangle. So we have opposite, we have hypotenuse, and we need adjacent. How do we find the adjacent side? By this Pythagorean theorem. We can solve for adjacent. The adjacent side will be the square root of what? This hypotenuse squared minus, because we need to subtract this opposite square from both sides to get that adjacent over there by itself, minus the opposite squared. So we can do that. Square root, hypotenuse is 13 squared minus opposite, which is 5 squared. 13 squared is 100 and 69 minus 25. Square root of 144, which is what? 12. And we take the what? The positive square root, because we're dealing with length, right? Dealing with length. Can't have negative length. So x is 12. So now that I know my opposite, adjacent, hypotenuse, I can go about finding the values of these trigonometric functions. So cosine theta is defined to be what? Adjacent over hypotenuse, 12 over 13. Sine theta. Sine is defined to be opposite over what? Hypotenuse. Tangent theta is what? Opposite over adjacent. And once we have these, we can easily find our other ones. Secant theta is a reciprocal function for what? Cosine. That's hypotenuse over adjacent. Cosecant is our reciprocal function for sine. That's hypotenuse over opposite. And cotangent is the reciprocal function of tangent. That will be adjacent over opposite. Okay? So if given a triangle where one of the lengths of a leg is missing, then we can find that leg by Pythagorean theorem, and we can evaluate these functions. Okay? We can evaluate these functions. Let's look at another example. Now we want to sketch a right triangle corresponding to cosine theta equally 5 over 7. Okay? We want to sketch a right triangle using this, and we want to use the Pythagorean theorem to determine the third side. I can't spell today for some reason. I can't spell. Most days it's that I can't add in my head. Today I can't spell. I'm like third, okay. All right, so we want to look at this. We're given that cosine theta equals 5 over 7. We want to use this to sketch a right triangle, and we want to find the third side as well as evaluate some of these trigonometric functions. Okay? So, cosine theta equaling 5 over 7. What does that mean for us? That means we know what? Okay? Cosine, we know hypotenuse and adjacent. The numerator represents what? Adjacent. The denominator represents the what? Hypotenuse. So that means we need to find the opposite side. okay? We need to find the opposite side. So, how do we find the opposite side? By Pythagorean theorem. The opposite side is what? Opposite will be the square root of what? The hypotenuse squared minus the adjacent squared. Is that correct? Okay, by using Pythagorean theorem, hypotenuse squared equals opposite squared plus adjacent squared. We can find the opposite. So what do we have? The opposite is hypotenuse squared, 7 squared, 49, minus the adjacent squared. The adjacent is 5, so 5 squared is 25. So this gives me the square root of 24. Now, let's talk about the square root of 24. Is that in its simplest form? No. And we want these radicals in their simplest form. How can we break down 24? 4 times 6. So the square root of 4 is 2. Square root of 6 is what? Simplified. So our answer here is 2 square root of 6. So x equals 2 square root of 6. So we're just going to pick a couple of these trigonometric functions to evaluate. We won't evaluate all 6. We already know what cosine is. How about sine? What is sine? Sine theta. Notice that we don't necessarily need to know what theta is, do we? We don't need to know what theta is. If we know these sides, doesn't matter to us what theta is. What is sine? Sine is opposite, which is 2 square root of 6 over hypotenuse, which is 7. Is that in the simplest form? Yes, it is. That's okay. How about cotangent? Cotangent is what? Adjacent over what? Opposite. Can I leave my answer like that? No. No, why? Right. A radical is not in its simplest form if we have a radical in the denominator. So we have to do what? Multiply by the square root of 6 over square root of 6. This gives me 5 square root of 6. What's the square root of 6 times square root of 6? 6. 6 times 2 is 12. So I may have to rationalize. Y'all remember that? Math 100? Rationalize my denominator to get that radical out. Okay? To get that radical out. Any questions so far? Any questions so far? Okay, let's switch gears a little bit. We're going to be looking at sine, cosine, and tangent of some special angles. As you work with trigonometry, you will notice that we have some special angles that, you won't even have to look at that back cover to find this sine or cosine value, or even have to plug in your calculator, because you'll work with them so much to where it will just become common knowledge to you. Okay? Now, of course, those quadrant angles, and we're not going to look at the quadrant angles, but the quadrant angles are what? 0, 90, 180, 270, and 360, okay? But other angles besides the quadrant angles, we're going to look at 30 degrees, 45 degrees, and 60 degrees, okay? We're going to look at those special angles and looking at their sine and cosine values and tangent values. So let's look at 30 degrees first. Sine, and if you want to, you can look at that back cover or that back page of your book that has that page, and we talk about that unit circle. But sine 30 degrees, in which 30 degrees is also pi over 6 in radians, that's defined to be 1/2. Cosine 30 degrees, or cosine pi over 6, is defined to be the square root of 3 over 2. Tangent 30 degrees or tangent pi over 6 is defined to be the square root of 3 over 3. Okay. Sine of 45 degrees, which you probably already know this one, which is sine pi over 4, square root of 2 over 2. Cosine 45 degrees, which is cosine pi over 4, is also square root of 2 over 2. And tangent 45 degrees, which is tangent pi over 4, is defined to be 1. And let's look at 60 degrees. Sine 60 degrees. 60 degrees is the same as pi over 3. It's defined to be the square root of 3 over 2. Cosine 60 degrees. Also cosine pi over 3 is defined to be 1/2. And tangent 60 degrees, which is also tangent pi over 3, is defined to be the square root of 3. So those are some of our common trigonometric functions, looking at 30 degrees, 45 degrees, 60 degrees. Now what we're about to do now, as I said last time, we showed you this sheet, which is one of the last pages in the book, and it has trigonometric identities on it, okay? And we're going over some of these trigonometric identities on this page, okay? On this page, they have the right triangle definition, they have the unit circle. Now we're about to talk about cofunction identities. That's also on this page. Cofunction identities. Now, this is going to help us also figure out certain values of trigonometric functions, and we'll look at some of this later. But some of these cofunction identities, sine of 90 degrees minus theta. And on this back cover, it may say sine of pi over 2, because pi over 2 is what? 90 degrees. Minus theta equals cosine theta. Tangent of 90 degrees minus theta equals cotangent theta. Secant of 90 degrees minus theta equals cosecant theta. Cosine 90 degrees minus theta equals sine theta. Cotangent of 90 degrees minus theta equals tangent theta. And cosecant 90 degrees minus theta equals secant theta. Notice cofunction. We have cosine, cotangent, and cosecant. Okay? These are our cofunctions. And they relate to, cosine relates to sine by a difference of 90 degrees in that angle. Cosecant relates to secant, and cotangent relates to tangent. Okay? Those are our cofunctions. We have some other trigonometric identities that we want to talk about. We can look at the reciprocal. I think we've already gone over these, but we'll make mention of them again. Okay? Sine theta, 1 over cosecant theta. Cosine theta, 1 over secant theta. Tangent theta, 1 over cotangent theta. We have made mention of these before, I believe, right? Well, they make mention again. Repetition does not hurt. It can help, right? And cotangent theta is 1 over tangent theta. All of those are on that sheet there, okay? These are reciprocal. We also have quotient identities. Tangent theta is sine theta divided by cosine theta. How are we to see that? Well, if we go back to what? Tangent theta being what? Is it y over x? Well, what is y? Sine. What is cosine? X. Okay? So, tangent is sine over cosine, which makes cotangent what? Cosine over sine. Okay? Those are quotients. Those are quotients. Okay, we have other Pythagorean identities that we can use with these trigonometric functions. We had the main Pythagorean identity that said what? Hypotenuse squared equals opposite squared plus, what was that? Adjacent squared. Well, we have other Pythagorean identities. That states sine squared theta plus cosine squared theta equals 1. 1 plus tangent squared theta equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. Now, why are we going over all these identities? Okay? Why are we going over all these identities? They will come in handy, Gabriel. They will come in handy. We are going to come to a section in a few minutes where we are going to be proving trigonometric identities. Proving that one side equals the other side, and what are we going to have to use? All these things that we've talked about here. Okay? And that's going to help us prove that something is a trigonometric identity. An identity. What is an identity? What is an identity? We have equations, we have identities, we have just statements, expressions. An identity means that something, whatever's on the left-hand side, we can do some work on the right-hand side and get the left-hand side to look exactly like the right-hand side. That's what an identity is. And we're going to look at some of those, not at this particular second, but we will look at some of these. We can also use these things that we've talked about to help us find function values. Okay? If we're given some things, some function values, maybe sine of some particular angle equaling something, then they may say, well, find cosine or find something. But we can use some of these properties to help us find those missing components. Let's look at an example. Let's look at an example. We want to use the function values and trigonometric identities to find the indicated trig functions. For example, first example we'll use these directions for a couple of examples, okay? The first example, suppose we are given that sine 30 degrees is 1/2 and we're given that tangent 30 degrees is the square root of 3 over 3. And we want to find cosecant 30 degrees. We want to find cotangent 60 degrees. And we want to find cosine 30 degrees. Okay? So, I'm given the sine value, I'm given the tangent value. How do I find cosecant? What do I know about cosecant? What can help me find cosecant? I'm going to let you think. I'm going to let you have some brain exercise today. Cosecant. Do I have, It's the reciprocal of the sine. So, cosecant theta is 1 over what? Sine theta, which is 1 over 1/2, which is what? 2. Okay? So, I have to use these identities. Maybe some of this stuff over here for me to find these things out. Okay? Now, the thought process will be, well, tangent. Do I have any identity that can relate tangent and cosecant? No, we don't. We don't. We don't have any of these things that we've gone over. And you can look at this back page. We've not gone over everything on this back page. But there's nothing really that we've talked about that relates tangent and cosecant. Then I move to sine. Well, yes, as he said over here, secant is the reciprocal function of sine. So this is a thought process. How about cotangent? 60 degrees.
What about 1 plus cotangent? Theta equals cosecant squared theta. You know. Oh, never mind. Sorry.
Okay. How about cotangent? That's okay. How about cotangent 60 degrees? Yes, it is reciprocal, but the angles are different. Angles are different. So what does that mean? Angles are different. The sum of those angles equal what? 90. So I may look at that cofunction stuff over there, huh? Right? Now, yes, tangent and cotangent are reciprocal functions, but that theta has to be the same, right? Tangent theta equals 1 over cotangent theta, the same theta. Here our thetas are different. But I notice, hey, the sum of those angles give me 90 degrees. So, what do I know about this cotangent and tangent? I know that tangent of 90 degrees minus theta is cotangent theta. I know that cotangent 90 degrees minus theta equals tangent theta. So, cotangent 60 degrees. I can think about this as tangent of what? 90 degrees minus 60 degrees, right? Right? 90 minus theta equals cotangent theta. But this tangent theta is still tangent of what?
30.
30 degrees, which is given to be what? Square root of 3 over 3.
Why is it 90 minus 30 is 60?
Okay, because we know the value of tangent of 30 degrees. And 90 minus 60 is 30, right? 90 minus 30 is 60. We have no idea. Well, that wasn't given to us in the problem. So you have to work with what's given and try to come up with something to fit what's given. Okay?
How do you use the tan?
How do we know use the tangent? Well, because looking at our cofunctions over there, we notice that this 60 and that 30 equals 90. Okay? Looking at our cotangent functions over here, tangent relates to cotangent, cotangent relates to tangent. So none of these others fit with these cotangent and tangent in the cofunction identities. Okay? Other questions? Are we getting some brain exercise today? How about cosine 30 degrees? Cosine 30 degrees. Now, I know you're thinking, well, how about that cofunction stuff over there, aren't you? No, because what? Cosine 30, sine 30, that does not give me 90 degrees. Okay, so I can't use that cofunction stuff. what else do I have that would relate sine and cosine? Well, let's look over here. I have something here that relates sine and cosine of the same angle, right? This Pythagorean identity. So, I know that what? Cosine. I can transform this equation to where I have cosine on one side. Cosine theta equals what? The square root of 1 minus sine squared theta. Right? Right, because we're squaring cosine here. And to solve for just cosine, we would have to take the square root. And it's not really theta, it's sine what? Theta is 30 degrees. Okay? So cosine 30 degrees equals the square root of 1 minus cosine squared theta. So, what is cosine theta? 30 degrees I should be saying. I should be saying sine. Gosh, sine 30 degrees is 1/2. And I need to square this, and when I square 1/2, what do I get? 1/4. Then I need to get, hey, what is 1 minus 1/4? Well, we should know that. 1 is the same as 4 over 4. Which is the square root of what? 3/4. Can I leave it like that, class?
No.
No, because what? It's not in simplest form if there's a fraction under radical, right? So I can break this up as the square root of 3 over the square root of 4, and the square root of 4 is what? 2. Okay? So I have to look at what's given and what it is they want me to find. Let's look at another example. The same directions here, but another example. Uh-huh. Because the reason is because they say using the information that's given. They want you to use the information. Now, on a test, am I going to really know? Well, I guess I will, because you will need to show your work. Use the information given, use these trigonometric identities to find this. This particular section that we're dealing with is not dealing with the unit circle. But yes, you could do that. That's a way to check your answers.
But it is up there, cosine 30 degrees.
It is.
If we knew that, then we would know the other.
Technically, yes. You would, okay? Yes.
Are we going to have all these little formulas for the test, or are we going to have to memorize them?
I don't know yet. I'm still thinking about it.
Because that's a lot of little things to...
Isn't it a lot to remember?
Same thing with the unit circle. Are we going to have the unit circle on the test?
You know, I'm thinking I'm going to let you use this little sheet here. I'm thinking I am, but don't hold me to that because I don't want to lie to you. It looks good.
Mine's all, yeah, it looks like the sheet I made for myself, except for a whole lot neater.
Yeah, it's that last page, right, that we talked about, just copied on a sheet of paper. But yeah, so more than likely, you know, I try to be reasonable, you know. I try to be a compassionate person most times, unless I'm made to be not so compassionate. So more than likely, you will have access to that page. We'll say more than likely, because if I change my mind, I don't want to say that I have lied to you. You know, teachers, they don't like to give people don't like to give direct answers, do they? Just talk all the way around the subject. All right, let's go back to our next example. We're given secant. Suppose we're given secant now. Same directions, but we are given secant theta equals 5 and tangent theta equals 2 square root of 6. And suppose they want us to find cosine theta, cotangent 90 degrees minus theta, and let's see. We'll just leave it here at these two. Okay, cosine theta. What do you want to use? Reciprocal. Reciprocal of cosine is what? 1 over secant theta, which means this is 1 over 5. How about this cotangent 90 degrees minus theta? What is that? Cofunction, but what cofunction is it? What do we have? Cotangent 90 degrees minus theta equals what? Tangent theta, which was given to be 2 square root of 6. Okay, y'all, we're going to move right along so that we can get through with this. Now, we want to use what I was talking about before. Use these trigonometric identities to show that they are identities, which means we're going to be given an equation and we want to make the right-hand side look like the left-hand side using these trigonometric identities. So we want to use trigonometric identities to transform the left side of the equation to the right side. Or you can do vice versa. You can transform the right side to look like the left side. The first one will be cosine theta times secant theta equals 1. So it's going to be feasible for us to work with this left-hand side and make the left-hand side look like 1. How do we do that? Let's think about secant. What is secant? Secant is what? 1 over cosine, isn't it? So I can replace secant with 1 over cosine theta equals 1. Well, my cosine thetas cancel, so I have 1 equals 1. So what I have shown is that this is a true identity. I have made the left-hand side, by putting in some identities, look like the right-hand side. 1 equals 1 is a true statement. Okay? Questions? I see some confused faces. You want to make the left-hand side, by plugging in an identity for something up there, look like the right-hand side. And if you make them equal, then we know, yes, this is an identity. Let's look at another one. Another example. Suppose we have cotangent alpha times sine alpha equals cosine alpha. Now let's think about this. I want to make this side look like cosine alpha. What could I use here? What could I use? Quotient. Cotangent theta equals what? Cosine over sine times our sine. I can cancel these out and I have cosine alpha equals what? Cosine alpha. So the thing is, you're going to have to look at these things, run through those formulas to see which one can I substitute in and possibly get me to what's on the right-hand side of that equation. And it does take time, and it takes a little bit of practice, okay?
What would you ever need to move things with?
Why would you need to do this? When you get to calculus 2 and you're doing integration, you may have something under something to integrate, which you probably don't know what integration is, but you may have something to integrate that's not easily integrable, which means that I may need to use some of these identities which can simplify that function, which gets me to something that I can integrate more easily. There is a use. It's not here, really. You know, all this is preparing us to go on to calculus 1, 2, and 3. So there are uses other places. Let's look at another one. 1 plus sine theta times 1 minus sine theta equals cosine squared theta. Now, you tell me, how do I want to start? How do I want to start? She's saying, I don't know how you want to start. I don't know how I tell you to start. But I want to work with this side. I really only have one equation up there that gives me something with cosine squared theta, right? That Pythagorean identity. So I need to make this kind of look like that Pythagorean identity. I can use FOIL and multiply all this stuff out, okay? When I do that, 1 times 1 is 1. I have minus sine theta plus sine theta, cancels out, right? Minus sine squared theta equals cosine squared theta. Well, looking at that Pythagorean identity, what is cosine squared theta? It is what? 1 minus sine squared theta. This comes from the Pythagorean identity, okay? It comes from the Pythagorean identity. Yes?
I thought the sine of theta cancel each other out.
The sine of theta.
When you multiplied it out, you said the positive not there.
But remember, FOIL, L means last. I have to multiply these two last terms. So sine theta times negative sine theta is negative sine squared theta. The inner and outer cancel. They cancel. No problem, because somebody else had that same question. They just didn't want to ask. So I encourage you to ask your questions. I encourage you to ask your questions. All right, let's look at another one. And we're not going to erase this here. We'll just go here. Keep our identities up there for the time being. Another example. Suppose we have sine squared theta minus cosine squared theta equals 2 sine squared theta minus 1. She says, oh my God, it'll be okay. And you want to make this side look like this side. Well, how in the world am I going to do that? Now let's think about this. We're dealing with squared thetas, you know, sine squared, cosine squared. Going right back to this Pythagorean identity, because this is really the only thing when we see sine squared, cosine squared. Okay? Notice on this left-hand side, I have sine squared, I have cosine squared. Over here, I only have sine squared. But can I not get an expression for cosine squared that I can replace into that function with sine squared?
You can wait.
Go ahead, Gabriel. Say what you want to say.
Sine squared theta minus sine squared theta, or is it sine squared theta minus? Does it matter?
Sine squared theta plus cosine squared theta is 1.
Yeah.
And what this means, and I think this is where you're trying to go, I can get that cosine squared theta is 1 minus sine squared theta. Is that where you're trying to go? I feel that's where Gabriel's trying to go. He's saying, I can get this equation in terms of cosine by subtracting sine squared theta from both sides. And I can in turn go up here and do what? Substitute. Okay? And that gets me a little closer. At least now, I only have the sine function on this left-hand side. Do we see that? Let's look back here. In the original problem, I have sine squared theta minus cosine squared theta on the left-hand side. And on the right-hand side, I have a sine squared theta. So, how can I kind of get rid of this cosine squared theta? Well, knowing that sine squared theta plus cosine squared theta is 1, I can subtract sine squared theta from both sides, and I can have an expression for cosine that I can do what? Replace here. Now what happens? I can distribute my negative to be negative 1 plus sine squared theta. I can combine like terms, sine squared theta plus sine squared theta. Two of those things, 2 sine squared theta minus 1 equals what? Equals 2 sine squared theta minus 1. And it takes time. It will take time. You know?
I understand the concept of it, but I don't think I can sit there and do it by myself yet.
That's where practice comes in. You're going to have to sit down and do, now if you remember, I do suggest that you do the odd problems. You may have to do the even problems, okay? You may have to do the even problems. And there should be a solutions guide to the even problems in our lab that you can go in and check your solutions. Okay, those resources are available to you. Okay? But no, I mean, I wouldn't expect you to just sit here and be like, okay, yeah. No, because I'm here to tell you how to think to do the problem. Okay? This is all we're really telling you to do. You know, what do I need to think about? Well, I have the sine squared on one side, the sine and the cosine squared on one side. On the other side, I have a sine squared. So let me try to get all sine squares in that problem. And how do I do that? Well, I look at my list of identities to see what do I have that relates sine squared and cosine squared. And this is the only thing that I have. This is one thing. Well, okay, how can I use that Pythagorean identity? Well, I can get an expression for for cosine and put it into that problem. And that's where our other cosine comes from. So it's really, you're really learning a thought process. You're really learning a thought process. How do I look at this problem and think about how to start it? And that's why I'm here. All right, let's look at another one. Let's talk about how we want to think about this problem. Okay. We have tangent beta plus cotangent beta divided by tangent beta equals cosecant squared beta. Go ahead and say it again. Oh my goodness, or whatever she said. So how do we start this problem? Let's think logically about starting this problem. I have a cosecant squared beta over there. Looking at my identities, cosecant squared beta. Where do I have a cosecant squared beta? Right here. 1 plus cotangent theta. So I need to think about, what can I do to that left-hand side there? Well, this says 1. And if I look, I have tangent beta over tangent beta. I can break this up. Let me break down this fraction. Tangent beta over tangent beta plus cotangent beta over tangent beta. I can do that. I can break a fraction up. Can I? I can do that. So what do I have here? Tangent beta over tangent beta is 1. That's 1. Now, cotangent beta over tangent beta, how does this break down? Cotangent over tangent. Okay, he said that they're reciprocal functions, and I can think about this as 1 over tangent beta times cotangent beta, right? He had the right idea, reciprocal functions. And what is 1 over tangent beta? Cotangent beta, isn't it? So now, yes, 1 plus what? Somebody said cotangent squared beta equals cosecant squared beta. So, I already know at this point I have the right answer because of what? This Pythagorean identity. But the directions told me to do what? Make the left-hand side look like the right-hand side. So 1 plus cotangent squared is what? Cosecant squared. Yes.
Problem on a test, we have to work that all the way down. But we already knew that it's 1 plus cotangent squared theta equals cosecant squared theta. We can just go ahead and replace that side of the fraction.
Okay. This is no, because this is the thing. You need to do the problem as if as if I don't know what you're doing. I'm just making your life more difficult on Gabriel. I need to learn somebody else's name besides Gabriel, because aren't you getting tired of me saying your name? Oh, okay. Question over here.
Questions like this, we're just going to automatically assume that it is going to come out to equal each other?
Right. I wouldn't give you a problem and tell you to, make the left-hand side look like the right-hand side if you couldn't do it. Now, I don't give tricky problems. Your problems will be straightforward. Huh?
I had the same question you had pretty much, because we have the concept right there. So if we know that's true, you can't just make the left side 1 plus cotangent squared theta.
You have to read what your directions tell you. If the directions say to make the left-hand side look like the right-hand side, then we can see it like this. But if it says if it just says show that they're identities, then this is okay. But if it specifically says, you have to read your directions, make the left-hand side look like the right-hand side, you need to go here with this 1 extra step. Does that answer the question? Now, I will say this, too, I know right now you think I'm very nitpicky. I'm really not that nitpicky, You will soon see. But you need to do these problems. I know most of us probably know some of this stuff. We have knowledge of these things. But in doing a test, I will say the more stuff you show, the more partial credit you'll get if you go the wrong way, If I can see your steps and I can see, okay, this is where he went wrong or she went wrong, you might get more partial credit if you just, okay, I know this in my head and I'm just going to write it down. I mean, I can see where you went wrong. And for that, you may get 0 partial credit.
So we should just assume that is a correct equation.
Well, it's a correct equation.
It's a correct equation. You just want to show.
We should assume that it's not, so we don't just jump straight to
Right. The more work you show, possibly, the more partial credit you'll get. Okay?
So they will equal each other, but we should assume that they won't.
Right. If that's the way you want to think about it. Whatever helps you think about it.
So it helps to, when you're doing it, it helps to break down the equation first if it's like a complex.
Right. It may help to break down. And being that you're not experienced in doing this, you may start off one way that will get you nowhere. And you may have to start over again and somehow get to a correct way to start. Because you may be thinking, okay, how do I know that I need to break that up? Well, it's trial and error. You may not know.
Because we know the answer already before we started.
Right.
That one has to equal that.
Mhm.
We know the answer already.
You just have to show me in an algebraically correct way, not make it up. I know y'all like to make up your own little things.
Yeah, I can show you where
I know. You can make me up something. So maybe I should preface with saying partial credit is given if you start on the correct path. in an algebraically correct way, and you somehow deviate a little bit, okay? You can't start off with wrong and end up with something right. And I know, you'll try to make it fit, won't you? Yes. So that's what I'm saying. Show your work. Show your work. That's right. Show your work. Are there any other questions before we go on to talk about something else? Okay. Couple of more problems. We want to solve for the indicated variable. First example. Suppose I am given this right triangle. I'm given that this angle is 60 degrees. I'm given that the hypotenuse is 18, and I need to find y. So I'm given an angle. I'm given the hypotenuse. I need to find the opposite side. I am not given the adjacent side. How do I want to start this problem? Sine, yes, sine 60 degrees. What is sine? Opposite over hypotenuse. And from here, I should be able to find y. What is sine 60 degrees? It's what? No, 60 degrees is pi over 3. What's sine? What's sine of pi over 3? A sine of square root of 3 over 2 equals y over 18. Can I solve this problem? Yes, I can multiply both sides by what? 18. So I have y equals 2 and 18 goes what? 9.
You use your calculator and you punch in the sine of 60 degrees, and how do you know that sine of 60 degrees?
Look on your unit circle.
Look on your unit circle, or you can punch in your calculator, because y also is equivalent to 15.59.
But if you punch it on a calculator, you get a straight answer.
What do you get, science? Well, remember, degree mode.
I got it in degree mode, and I came up with 0.86602.
Okay, times 18?
Times 18.
Yeah, what is that?
15.5. Oh, hey, I didn't see you.
Okay, so.
What form do you want us to set it in?
You know, I don't really, well, I need to probably clean it up. I was going to say I don't really care, but it depends, because sometimes it may say, give me an exact value. And if it says, it depends on your directions. You have to read. If it says, give me an exact value, then I'm going to choose this one. If it doesn't specify, you can give that. Yes?
What is it? We put it in radians?
When there is no degree symbol, it can say radians, or it can say nothing then. Like it could just say pi over 3. That's right. It could just say 2. If it just says 2 and there is no degree symbol, it's assumed to be radians. So whenever there's no degree symbol, radians. Other questions? Okay. This will be all that we'll talk about today.
I was just about to ask you when we could go.
You were?
Yeah, it was like perfect timing.
Okay, we will end it here today, and we'll talk about trigonometric functions of any angle on next time.